So hello everyone. So welcome back. And now in the last lecture of states of matter, we have solved 13 questions of the exercise. Now we'll be starting with the rest of the questions of the exercise. So let us start with question number 5.14. So in the question, how much time would it take to distribute one Avogadro number of wheat grains if 10 to the power of 10 grains are distributed each second? Okay. So we have asked that how much time you need to distribute one Avogadro number of something like here wheat grain to distribute. When you are distributing, what is the rate of distribution right now? It is given as 10 to the power of 10 grains you're distributing in 1 second. So how many times you will need to distribute one Avogadro number? Okay, this is very simple unitary method question. So we will do it as like this. So we know that one Avogadro number is equals to 6.022 into 10 to the power of 23, right? And we know what is the rate of distribution. That is, for 1 second, you are distributing 10 to the power of 10 grains. So how much time you need? Okay, so that means you need to distribute this much of grains. Okay, so how you calculate it is that 1 upon 10 to the power of 10, that is for how in 1 second how much you're doing and how much time you need to distribute 6.022 into 10 to the power of 23. You can calculate it by doing it like this only. So you have to divide 6.022 into 10 to the power of 23 upon 10 to the power of 10. So that will give you the number of time, the number of seconds you need to distribute the Avogadro number of grains, and it will come, it as answer will be 6.022 into 10 to the power of 13 seconds. It was just a simple unitary method to solve the question. So let us move forward to the next question, which is question 5.15. So calculate the total pressure in a mixture of 8 gram of dioxygen and 4 gram of dihydrogen confined in a vessel of 1 decimeter cube at 27 degrees centigrade. And also they have given you R. So what we have to calculate? We have to calculate the total pressure. So how you can do it? So they have given you the volume, they have given you the temperature, and they have given you the R value also. So what you'll do, you calculate separately the pressure of both the gases, and then you'll add up, because anyways they are asking for the total pressure. So they have given also that you have 8 gram of oxygen, you have 4 gram of hydrogen. So first you'll calculate the pressure exerted for this values by 8 gram of oxygen, and then second after that we'll calculate the pressure exerted by these values by 4 gram of hydrogen. So first of all, we can calculate this gram to number of moles we can calculate for each dioxygen and hydrogen. So this is how we are calculating the number of moles of oxygen, and it will be equal to the mass upon molecular weight. So it is equal to 8 upon 32 moles. And similarly for hydrogen, you'll have 4 upon 2. So now you will calculate separately, right? Or what you can do is that there are two ways. You can calculate separately by introducing number of moles of oxygen one time and calculating the pressure, and then introducing the number of moles of hydrogen one time and calculating the pressure exerted by hydrogen. You can add it up. And the second thing, what you can do is that you can just add the number of moles and you get the total number of moles. Okay. So when you have to just add the total number of moles. So here, this is what I have shown. So what I have done is that if I replace N by NT, that is the total number of moles. So here P will be replaced by total number of pressure, the total pressure also. So I'm just doing in one go. So I have added the 2 moles of oxygen and hydrogen. So that is equal to 8 upon 32 plus 4 upon 32, and just given the values, substitute the values of the variables, and then we got the total pressure, that is equals to 56.025 bars. This is the answer. We can do in that way also, like separately calculating and then adding. So that will also land you in the same answer. So I hope that it is clear. So let us move further to the next question, question number 5.16. So what they asked, payload is defined as the difference between the mass of the displaced air and the mass of the balloon. Okay, so we have to calculate the payload That is the difference between the mass of the displaced air and the mass of the balloon. When a balloon of radius 10 meters, mass 100 kg, is filled with helium at 1.66 bar at 27 degrees centigrade. Also, they have mentioned the density of air and value of R. So, for such big questions, you don't have to panic. First of all, you have to note down what they have given. So, first, they have given the radius of the balloon, which is 10 meters. So, you will, from that balloon radius, you will calculate the volume. Okay. So you can easily calculate the volume of the balloon because it is spherical in shape. So we can apply the formula for this volume of sphere, that is 4 upon 3 into pi r cube, right? So when we put the values, we get the volume of the balloon. Okay, and also they have mentioned the mass of the balloon. So mass of the balloon, volume of the balloon is clear. Okay, we know that they have filled helium in the balloon, and volume of helium is nothing but the volume of balloon only. So in this state of equation, where you have to calculate the mass of helium in that balloon. So you can easily calculate it by using the state equation, that is PV equals to nRT, where you can easily substitute number of moles by mass upon molecular weight. For helium, you know the molecular weight, right? It is 4. And also in this question, do not forget to convert all into the SI units. Okay, so here 4 gram I have converted into 4 kgs. So that is how you do. Also, here I think it is clear. Okay, so when you substitute all the values of PV and M and R and T, you can get the mass of the helium. So now, what is the mass of the balloon now when you fill the helium? So it is the mass of the empty balloon that was already given as 100 kg and mass of the helium that you just calculated. So there we got the mass of the total balloon, that is equals to 1216.4 kgs. Now, what is they have asked is what is the mass of the displaced air? Okay. And also they have mentioned the density. So density into volume. So how much displacement will be there of the air will be equal to the density is given, right? So you need to calculate what? You need to calculate the mass of the air that is they have asked. So you can easily calculate it by just multiplying density into the volume of the sphere. So density is 1.2 and volume of the sphere was 4.86. So this is the mass of the displaced air, okay? But in the question, what they have asked? Payload. So they have also told in the question what is the definition of payload. So they have mentioned, one second. So they have mentioned that payload is defined as the difference between mass of the displaced air and mass of the balloon. So we now know that the mass of the final balloon, like helium plus mass of balloon, and also we now know that what's the mass of the displaced air. Now if we subtract it, then we can find out the payload. So the payload here is 5024 minus 1216.4 kgs, and hence the answer will be 3807.6 kgs. This question was quite tricky, but a very good question. So let us move forward to the next question. This question number 5.17. The question I asked for: calculate the volume occupied by 8.8 gram of carbon dioxide at 31.1 degrees centigrade and 1 bar pressure. And R is also given. So this is a very straightforward question using that we will solve using the state equation. We just have to modify it because they had given the mass, okay, and they have asked for the volume. So they have not given the number of moles, but you can easily find out the number of moles if they are given a number of mass and identification of the gas. Here it is carbon dioxide. So you already can calculate the number of moles by dividing the mass given and divided by the molecular weight of the carbon dioxide, which you already know. It is 44. So temperature is also given. Do not forget to convert degree centigrade to Kelvin when you are solving for states of matter, because in all the equation only Kelvin holds, and because you have the value of R in that you have Kelvin only. So you have to take into consideration that in the value of R, if you have bar, you have liter, you have Kelvin, you have mole, then you have to convert your pressure if it is given in Pascal or any other units. You have to convert it into bar and then solve. For temperature similar, you have to convert it into Kelvin then solve. For volume also you have to calculate into convert into liters and then solve. So when you put all of these values into PV is equals to nRT, then the volume that you will get will also be in liters. Okay. So when you put all the equation values in this equation, you will get the answer as 5.05 liters. Now let us go to the next question. Question number 5.18. 2.9 gram of a gas at 95 degrees centigrade occupied the same volume as 0.184 gram of dihydrogen at 70 degrees centigrade at the same pressure. What is the molecular mass of the gas? So what is given here? What you have to calculate? Sorry, I lost the connection. I'm resuming it. Yes. So in question number 5.1, if we were there, so they have given that 2.9 gram of gas at 95 degrees centigrade occupies the same volume as 0.184 gas of dihydrogen at 17 degrees centigrade. So from the first equation of 2.9 gram of gas, okay, was the same volume as 0.184 gram of dihydrogen at 17 degrees centigrade at the same pressure. So you have to keep the pressure constant as P. Okay. So for P, first you have to calculate the volume occupied by hydrogen. So if you calculate the volume occupied by the hydrogen, because both the gases are occupying the same volume. Okay. So what you can do is that you apply this state of equation P is equals to nRT for hydrogen. So for hydrogen, you can use to calculate the volume occupied. So here they have mentioned also that you have for 0.184 gram. So you have to calculate the number of moles by dividing it by 2, which is the molecular mass of dihydrogen. And here for simplicity, we are keeping the values of R and P at R and P. P is already not given, but the pressure is constant. And R is a constant only. So we are not putting any values to it because at last we will cancel them out. And temperature is given as 290 degree. So 290 Kelvin. So this volume we got it as 26.68 R upon P. Now the question is already told that the volume occupied the gas X that for which you need to calculate the molecular mass is equal to the volume occupied by hydrogen, that is equal to 26.68 R upon P. Right? So if we put the values of that at a different temperature of 368 Kelvin. So if we put the value of P, then you can actually find an substitute number of moles by mass upon molecular weight because mass of the gas is also given. So if you put it, then you see that pressure is getting cancelled, R definitely is getting cancelled, and you are left with only one variable, that is molecular mass. And from that equation, by solving this equation, you can actually find out the answer of molecular mass, which comes out to be 40 gram per mole. Let's move to the next question, question number 5.19. So a mixture of dihydrogen and dioxygen at 1 bar pressure contains 20% by weight of dihydrogen. Calculate the partial pressure of the dihydrogen. Okay. So what they have told that you have in a container mixture of dihydrogen and dioxygen. Okay. And in this mixture, the total pressure of this mixture is 1 bar. And also they mentioned the hydrogen in that mixture is 20% by weight. So that simply means if you have 100 gram of gas, and that 20 gram is dihydrogen and 80 grams is oxygen. Okay. But what you have to calculate here is the pressure of dihydrogen. So total pressure it has given, but you have to calculate the pressure of the dihydrogen. So we know that the partial pressure equals to the moles fraction into total pressure. Total pressure is also given. You have to find out the partial pressure of dihydrogen. So if you know the mole fraction for dihydrogen, then you can actually find out the partial pressure for dihydrogen. Okay. So mole fraction, how you can find out? So from this, you can easily find out. So they are given that dihydrogen is 28%. Okay. So we can consider eating this one. So 100%, that means in 100, right? Among 100. So in 100 gram, so 20 gram is hydrogen and 80 gram is oxygen. So here, from here, you can actually calculate. So we know that molecular mole fraction of hydrogen will be equal to the number of moles of hydrogen upon total number of moles. So 20 upon 2, which is the molecular mass of hydrogen, upon 20 upon 2 plus 80 upon 32. That is the oxygen. So you get the value as 10 upon 12.5. So this is the molecular fraction or mole fraction of hydrogen. So if you substitute this value to this equation of partial pressure of hydrogen, and then you can easily get the answer as 0.8 bar. So let us move forward to the next question, which is question number 5.20, where you have to find out the SI unit of this value, PV squared T square upon N. What would be the SI unit of the quantity PV squared T square upon N? So first of all, you need to know the SI unit of all of this single entities. So for pressure, the SI unit is Newton per meter square. For volume, the SI unit is meter cube. For temperature, the SI unit is Kelvin, and for N, the SI unit is mole. So you substitute all here. So Newton per meter square into meter cube upon 2, because it is also 2, and Kelvin to the power of 2 upon mole. So when you add it up and cancel and solve this equation, you will reach to this value where the answer is Newton meter to the power of 4 Kelvin square per mole. That is the answer. Let us move forward to the next question, which is question number 5.21. We are almost completed. So in terms of Charles' law, explain why minus 273 Kelvin centigrade is the lowest possible temperature. So this is the on the first place, this question is already discussed while I was teaching. That why, and also you saw that in the derivation you get this, right? That the minimum temperature that can be attained is minus 273 degrees centigrade. So this is the graph of the Charles law. So the graph is in the y-axis you have volume, in the x-axis you have the temperature. After that, so, and this is a straight line, and this line touches this x-axis at where the temperature value is minus 273 degrees centigrade. So from this graph, it is very, very clear that at this temperature, the volume of the gas is 0. And you know that below this temperature, the volume of the gas cannot be negative. Volume of anything cannot be negative, right? So that is why this temperature is the limiting temperature. So below this, the temperature cannot exist. So this was the logical explanation, and derivation we already discussed while teaching. So let us move forward to the second last question of this chapters, that is the state of matter, question number 5.22. It's a very simple question. Critical temperature for carbon dioxide and methane are 31.1 degrees centigrade and minus 81.9 degrees centigrade respectively. Which of these has stronger intermolecular forces and why? Okay, fine. So, first of all, you need to understand the question, and then you can easily, there's no solving. It is just a reasoning question. So they have mentioned the critical temperature. So, and they have asked that in which gas the intermolecular force is higher. So we know that that below critical temperature, any gas liquefies. So that means whoever gas has critical temperature more, like more, right? More positive, that will liquefy first. Okay, so when you are going from 50 degrees centigrade to the negative of the temperature, you're decreasing the temperature. That is, you're making the more the intermolecular forces. So at 31 degrees centigrade, when you reach, so in that case, carbon dioxide liquefy, but still the another gas, that is the methane, did not liquefy. And when you reach the temperature of minus 81.9 degrees centigrade, then only methane liquefied. So that means that which has the more intermolecular forces? So that gas has more intermolecular force of attraction, that liquefies first. So whose critical temperature is greater will liquefy first, and hence it will have more intermolecular force of attraction. And that is why it is liquefying first. So in here, since the critical temperature of carbon dioxide is more than that of methane, that is why carbon dioxide has more intermolecular forces. So that is the answer. So let us move to the last question of this chapter, question number 5.23. It is given, explain the physical significance of Van der Waals parameter. So Van der Waals parameter is A and B. So we have studied the equation of state PV equals to nRT is for ideal gas. But when we are talking about real gas, so this real gas equation comes into picture where we have two Van der Waals parameter. First is A and second is the B. Okay. So this is the modified equation of state, which is P plus A n square upon B square into V minus NB equals to nRT. So this is this term comes from the intermolecular forces. Okay. So here in real gas, you have some intermolecular forces, right? So that is getting added up because in ideal gases, there is no intermolecular forces, and hence this parameter is 0. But in real gas, you have intermolecular forces. So this parameter A corresponds to the intermolecular forces that exists between the atoms in the real gas. And the second equation, that the second Van der Waals parameter is B, which contributes to the size of the molecules in the real gas. Because in case of ideal gas, we consider that the size of the atoms or the molecules is negligible in comparison to the volume of the container. But in real sense, the volume of those atoms and molecules has to be considered, and that is why we subtract it. Okay, that is not negligible, and that is why we subtract it. So B corresponds to the size of the molecule of the real gas. I hope that this two lectures is useful to you because we have solved each question of this exercise in details, and I hope that your doubts are clear by now for this stage of matter. So thank you everyone.